All right, let's dive into something that, let's be honest, can feel a little intimidating: algebra. We're going to demystify the whole thing, and I promise by the end of this, you'll see it's nowhere near as scary as it looks.
So this is the big one, right? The question everybody asks. You're going along just fine with numbers, everything is adding up, and then bam! All of a sudden, the alphabet just crashes the party. So what happened? Well, it turns out those letters, they're the secret key to a whole new level of math.
And here's a little secret: you're already using algebra. You do it all the time. I mean, think about setting your alarm clock. You do this quick mental calculation, right? Okay, I need time to shower, time for breakfast, time to get to work. You're using these unknown amounts of time to solve a problem. See? You're already thinking algebraically. So here's our game plan. First, we're going to break down what algebra even is. Then we'll hit that big question: why the letters? After that, we'll take a quick trip back in time to see how we went from words to symbols. And we'll wrap up by looking at some super common traps and, more importantly, how to sidestep them.
Okay, first things first. Let's get right to the heart of it. What are we actually talking about when we say the word algebra?
At its core, it's really this simple. Algebra is just a way for us to use symbols, usually letters, to talk about numbers we don't know yet or numbers that can change. It's basically the language of relationships.
And that language is built on two really key ideas. On one side, you've got your variables. Those are the letters, like X or Y, and their whole job is to represent values that can change. Then on the other side, you've got constants. Those are your plain old numbers, like 4 or 26. They're fixed. They are what they are.
And that brings us to the main event. Why do we even bother with letters? We have plenty of numbers. They work just fine. So what's the deal? Well, it's because letters give us a kind of mathematical superpower. They let us go from solving one single, specific problem to creating a general rule that works for any situation every single time. It's a total game changer. A perfect example is the area of a rectangle. Area equals length times width. A equals L times W. That little formula is pure algebra. And it doesn't matter if you're talking about a rectangle the size of your phone screen or one the size of a city block. That one rule works for all of them. That's the power of using letters. So yeah, the letters aren't there to make things harder. They're there to represent unknowns, to help us create these big general ideas, to build a foundation for more advanced stuff like calculus, and to create this universal language that scientists and mathematicians all over the world can use.
So, where did this language even come from? I mean, it didn't just pop up out of nowhere. It's actually been evolving for thousands of years.
The journey really started almost 4,000 years ago. The ancient Babylonians would write out their math problems entirely in words. Then, around 820 AD, a Persian mathematician named Al-Khwarizmi literally wrote the book on how to solve equations systematically. His name even gave us the word algebra. But it wasn't really until the 1500s that a guy named Francois Viet helped make using symbols the standard, creating the kind of algebra we see today.
Just to give you an idea of what that was like, instead of writing something clean like x plus 5 equals 8, they'd write out the whole sentence: the thing plus 5 equal to 8. Can you imagine trying to do your homework like that? It really makes you appreciate how elegant and simple x is.
Okay, we've talked about what it is and why it's useful. Now for the super practical part. Let's go over a few of the most common mistakes, little brain glitches really, that people make in algebra and how you can spot them and avoid them.
All right, first up is what I like to call the distribution glitch. It's so tempting, and almost everyone does it at some point. It's when you see an exponent and you just want to sprinkle it onto everything inside the parentheses. Here it is in the wild. The mistake is thinking that x plus y squared is the same as x squared plus y squared. It's just not. Remember, squaring something means multiplying it by itself. So x plus y squared is really x plus y times x plus y. And when you work that all out, you get that pesky middle term, 2xy. Don't forget the middle term. So next up, we have a very similar kind of mistake, but this time with square roots, or radicals. The mental shortcut feels the same, just apply the operation to each part inside. But again, it's a trap. You simply cannot distribute a square root across addition or subtraction. The square root of x squared plus y squared does not and will never equal x plus y. Think of that plus sign under the radical as superglue. It holds x squared and y squared together, and you can't break them apart.
And for our last trap, we have the cancellation error. This is what happens when you've got a fraction and you get a little too happy canceling things out from the top and the bottom.
It's so tempting to just cross out the a's here, right? But you can't do it. Why? Because that a on top is part of a sum. It's being added to b. The rule is simple. You can only cancel common factors, things that are being multiplied by the entire top and the entire bottom.
So after all of that, what's the big takeaway? If you only remember one thing, let it be this. Algebra isn't just a random set of rules you have to memorize for a test. It's a language. And it's an incredibly powerful language. It's the language we use to describe patterns in the world, to talk about things we don't know yet, and to build these amazing general solutions that can solve a million problems all at once. It's really a tool for thinking more clearly.
So once you start seeing it that way, as a language for modeling the world around you, it stops being about memorizing rules and starts being about creative problem solving. So I'll leave you with this question. What problem are you going to solve with it?